Hey guys, what's up? We're doing this lecture on video instead of live stream because I had some technical difficulties earlier in the day. So just gonna knock this out and move on with chapter 14 today. And the section is called 14.1 Functions of Several Variables. And it's basically just gonna like take everything you know already about functions and scale it up to multivariable functions. So recall in single variable calculus and pre-calculus and all that stuff, we had something like y equals f of x, and x was the independent variable. So x was the independent variable, y is called the dependent variable. And the function has a domain, so domain D is the set of all valid inputs for f of x, and the range R is the set of all possible outputs. So all possible outputs. So you have one number go in, you have one number come out, and that's a function of one variable. That's a real valued function of one variable. So what we're going to do today is consider the possibility of more than one variable going in, but still just one real number coming out. So today, we consider z equals f of x and y, where here x and y are the independent variables, so x and y are independent variables, meaning there's no relationship between them. If you vary x, y is not going to change at all. All right, so there's no relationship. There's no way to know what y is going to do if x does something. Z is now going to be the dependent variable. So ordered pairs x, y get mapped to real numbers z. So this lives in the two-dimensional space, and this just lives in the one-dimensional space. So the inputs are ordered pairs, the outputs are real numbers on the real line. So now the domain is a set of ordered pairs instead of just a set of real numbers. So the domain may look something like this. And so all possible inputs are something inside this set D, and then those ordered pairs get mapped through the function f of x and y to some number on the real line, f of xy. So that's the visualization now, if you will. So now D is the set of all ordered pairs. So domain D is the set of all ordered pairs xy such that f of xy is a valid expression. So that's what domain means now. It's pretty much the same thing. The function has to be defined. So it can't be, like the normal stuff. Radicals, even radicals need to be non-negative. Natural log or log functions need to be positive. So stuff like that. We just got to avoid those scenarios. But it's pretty much the same idea. We just have numbers going in and now more than one number. So x and y both go in to the function, and then a real number comes out. There are many examples of this, one being just, first of all, like a grade in a class. Like in this class, your final grade is determined by 3 exams, a final, and a homework score. So that's 5 variables that can change your final overall percentage. So it's like a function of 5 variables. So there are plenty of like real world examples of multiple things going in, one number comes out. So this is kind of the idea that we want to take away. We want to go into chapter 14, multivariable functions, and then multiple integrations whenever we get to chapter 15. So it's going to be pretty much the rest of your calculus career is dealing with these multivariable functions. And then we get to even more complicated multivariable functions when we get to chapter 16 eventually. So anyway, example, sketch the domain of the functions. So example, sketch the domain. Sketch the domain of the functions. And we have 2 functions here. The first one is f of xy equals x times natural log of y. And the second one is the function g of x and y equals 2x over the square root of y minus x squared. So we've got 2 functions here. We want to find and sketch their domains. So solution. Let's see. Just want to make some notes. Even radicals. So even radicals must have non-negative terms. Underneath them. So underneath the radical. So that's just a common thing. So square roots, 4th roots, 6th roots, etc. They have to have non-negative terms under the radical for that to be a valid output. In this class, right, there could be like a complex number that comes out, but that's a different class entirely. That's complex variables calculus. So we're not worried about that. We're only worried about real valued functions, not complex valued functions. So we're going to stay away from that. The second thing to note is that logs, so logarithms, logarithmic input must be positive. So those are like the 2 probably most important things that you'll come across when you're trying to find domain of a function. It's either log or radical or something like that. And for a logarithmic function, the input has to be positive. So we got that in mind. Let's do part A. Part A says f of xy is equal to x times natural log of y. Well, x is fine. The natural log of y requires that y be greater than 0. So x can be anything. So if that's the case, if we just need y to be greater than 0 and x can be anything, well then draw xy axis here, then the domain does not include the x-axis, but everything above the x-axis where y is greater than 0. So the domain D is equal to the set of all ordered pairs xy such that y is greater than 0, which is everything in the top half plane, not including the x-axis. So the top half of the plane, but not including the x-axis. So everything above the x-axis is the domain for this function. I can take any ordered pair up there, plug it into the function f, and get an output. Part B. g of xy equals 2x over square root of y minus x squared. Oh, I forgot probably the most important one. Cannot have 0 in the denominator. So you cannot have 0 in the denominator, of course. So this one, the radical would tell us y minus x squared should be greater or equal to 0, right? It has to be non-negative, but cannot equal 0 since in the denominator. So we have to have y greater than x squared, basically. So the domain D is the set of all ordered pairs xy such that y is greater than x squared. And graphically, you draw the parabola y equals x squared and then pick all the y values larger than y equals x squared. So I'll do a dotted line here for y equals x squared. And then everything above that, so all the y values above that are included in the domain for this function. So that is going to be our answer. So here are our domains, and then we've also sketched those domains. So I'll just try to slow down a little bit. Make sure everybody's able to write things down. Of course, you can pause as needed. Everything is similar for functions of 3 variables. So everything is similar for maybe something w equals f of x, y, z. Right, so for w equals f of x, y, z, you have a function of 3 variables. X, y, and z are independent. W is dependent. So then the domain is some portion of 3-dimensional space. So the domain D is some subset of the 3-dimensional space. So again, the same thing applies. No 0 in the denominator. Things under the radical must be non-negative, and natural log inputs must be positive. There are other crazy functions that we could worry about, but we're not going to worry about them for the most part. So for example, find and describe the domain of g of x, y, z equals square root of 9 minus x squared minus y squared minus z squared. So find the domain and then describe it. So kind of give an idea of what it would look like. So if this is the function, then what do I need? I need the radical. It's an even radical, square root. I need the input 9 minus x squared minus y squared minus z squared. I need that to be greater than or equal to 0, which means I need x squared plus y squared plus z squared to be less than or equal to 9. So that's everything inside and on the sphere of radius 3 centered at the origin. So D is going to be the set of all triples x, y, z such that x squared plus y squared plus z squared is less than or equal to 9. So this is everything inside and on the surface of the ball of radius 3 centered at the origin. We could draw that, of course, in three-dimensional space. And that would be our domain D. And here the surface of the ball, or the edge, or the, what do we call that? The boundary of the ball is included in this case because we have that equal sign available to us. So that would be the domain of the function of three variables. So cool. The next thing I want to do is talk about level curves and contour plots and things like that. So actually I'll link you to a video of some good graphical things that I've done with that already. But here I want to give you some more technical definitions and things like that. But that other video, I'll link to it right here, is a very visually motivated video, very visually stimulating, nice contour plots and things like that to kind of get the idea of like being able to like see the shapes and relate them to their contour plots. It's kind of hard for me to draw it sometimes. So I think that's a good video for actually seeing them. But I'll try to do a good example here, at least that I can draw, and then I'll link you to that video. So definition: a level curve of f of xy is the two-dimensional graph of f of xy equals a constant. So a level curve is really just a two-dimensional graph when you set f of xy equal to a constant. So where c is some constant, where c is some constant in the range of f. Of xy. And then a contour plot of f of xy is a graph of numerous level curves. So a contour plot is just a bunch of level curves all graphed together. A level curve is just a two-dimensional cross-section, basically, of a plane with your surface. So, for example, let's say I have the function z equals x squared plus y squared. We know that's a paraboloid, so I'll try to draw that paraboloid here. So the paraboloid z equals f of xy equals x squared plus y squared looks something like this. Well, I probably have drawn it not very well, but cut me a little slack. So if I plot some level curves, let's say I pick z equals 0. So if I pick z equals 0, that's equal to x squared plus y squared. That's just a point right here. That's z equals 0. What if I pick z equals 1 equals x squared plus y squared? Let me color code them a little better. So let me make them different colors so we can kind of trace them. So if I pick z equals 1 equals x squared plus y squared, then I get a circle of radius 1 centered at the origin. So that's everything on that circle corresponds to a z value of 1, or a height of 1. So that's z equals 1, corresponding to this curve. If I pick z equals 2, so z equals 2, maybe I should pick not 2 but 4, z equals 4, x squared plus y squared. So that's like somewhere up here. As z equals 4. So that's a circle of radius 2. You can forgive my circles. Everything on this has a value of z equals 4. And we could pick z equals 9. But what's the radius of the circle? The radius of the circle here is 1. The radius of this circle is 2. The radius of this circle is 0. But the z value on the paraboloid is higher than just 1, 0, 1, and 2. It's 0, 1 squared, 2 squared. So the connection is that this trace on my surface maps to this level curve. So it's basically just looking at it from one direction. In this case, looking at it from the positive z direction, you would see these curves kind of inside of each other, looking down into the bowl. So that is the idea of contour plot. So there is something to note specifically about contour plots. So I just want to make one remark. And that remark is that blank space in a contour plot corresponds to a region of slow change in the function values. Tightly packed regions of curves represent rapid change in the function. So just some things to keep in mind when you're looking at contour plots. Those are going to be pretty common. You'll see like in a contour plot, you'll see a whole bunch of curves really close together, and then you'll see spaces between curves. So where the curves are really close together, the function's doing a lot of crazy stuff, like going up super steep or dropping down super steeply or going up and down a lot. I don't know, it just depends. But if there's spaces where it kind of or if there are sections where there are a lot of space between the curves, then it's like, oh, the function is not really changing a whole lot. So it actually has to do a little bit with the, sneak preview, the derivative, the partial derivatives of the functions in those directions. So the rates of change of those functions in those directions. So now we want to get into the calculus of these functions, and that's where we bring in limits and continuity. All right, so limits and continuity are going to talk about, basically how you get closer and closer to a point x, y. What is the function going to do? So just recall, for a function of one variable y equals f of x, what did it mean to take the limit as x goes to a, f of x? So limit f of x as x goes to a meant, or equals L meant that as x got close to A, then f of x got close to L. So let's say there's a function. Let's say it's open there, and this is the point A, and then this is the point L. And this is y equals f of x. And we know from single variable calculus that you could go to A from the right, so x goes to A from the right, or you could approach from the left, so x goes to A from the left. Either way, you should get this limit L, and that was actually a way that we test for the fact that there may not be a limit, is we tried to show that the left and the right limits were not the same, and then we were able to show that the limit did not exist. Furthermore, if we showed that they were the same, then we could claim that it does exist. Well, that's actually not going to be the case for us now, because we're going to approach a point xy in the two-dimensional space, and as we get closer and closer to xy, the function value should get closer and closer to some point L. However, how do you say approach a point in two-dimensional space? And how do you say that precisely? So that's going to be our first thing that we have to get a handle on, and that's our definition. So definition for the limit of a function. So let f be a function of two variables. So let f be a function of two variables with domain D. Then if every then if for every epsilon greater than 0, there is a delta greater than 0, such that if the point xy is in D, the domain is in the domain of f, where square root of x minus a squared plus y minus b squared less than delta implies absolute value f of xy minus L less than epsilon, then we say f of xy has a limit at the point AB, and we write limit as xy goes to AB, f of xy equals L. So there's a lot going on in this definition, but probably the takeaways are the point that you're finding the limit at is the point AB, which may or may not be in the domain of f, but you're somehow approaching that using this circle of radius delta. So if I get to within a circle of radius delta to the point AB, and that implies that f of xy minus L is less than some point epsilon, any value epsilon, then we say that L is the limit of the function f at the point AB. So let me try to graphically represent this for you. So in the xy domain, you have some points right here, AB. So that's your point AB. And over here you have your real line. And let's say this is L. This is the point L. And the first thing you do is determine epsilon. So determine how small to make epsilon. So determine epsilon. Once you do that, you get this range of L plus epsilon and L minus epsilon. Once you know how close you want to be to L, you should then be able to determine a circle of radius delta around the point AB such that you pick any point in there, xy, then f of xy will be somewhere in here, in this interval L minus epsilon to L plus epsilon. So determine epsilon, find delta. We can guarantee that L minus epsilon will be less than or equal to f of xy less than or equal to L plus epsilon if L is the limit, or a limit, but it's unique. If L is the limit of f of xy at the point AB. So that's what it means to have a limit for a multivariable function. Very complicated. It's not a super friendly thing to look at necessarily, but it's the best we can do, to be honest. So let's just think about this for a second. So recall, for y equals f of x, number one, to show the limit does not exist, we showed that the limit as x went to a from the right, f of x was not equal to the limit as x goes to a from the left, f of x. Number two, to show limit as x goes to a, f of x equals L, we showed that the limit as x goes to a from the right equals L, and the limit x goes to a from the left equals L. So one of these will transfer over to multivariable functions, but the other will not. So think about our circle of radius delta up here. You know, our circle of radius delta. How can we approach this point AB? Well, we can approach it from the right. We can approach it from the left. Well, we can actually approach it from top, and we can actually approach it from the bottom. We can actually approach it any way we want to. So for us, in multivariable functions, there are infinitely many paths to get to AB. So now there are infinitely many paths to take to our point AB. So there are two takeaways from this statement. The two takeaways are the limit, if it exists. So number one, the limit, if it exists, must be the same. So must be the same regardless of path. So regardless of path taken. So that makes sense, right? That was kind of like the first thing we said, you know, over here. To show the limit did not exist, we showed that the paths gave different answers. Well, that's what we're going to do here. So basically, the takeaway is going to be that if two paths yield different limits, then we can claim the limit does not exist. However, number 2, we cannot claim the limit exists by showing it is the same for a few paths. So that's extremely important. We cannot claim that the limit exists. So we cannot claim the limit exists by showing it is the same for a few paths. There are infinitely many paths that approach this point AB. So we'd have to show that every possible path, which we can't because there are infinitely many, every possible path yields the same limit. So that's a problem. And we're going to remedy that with continuity next time, I think. So we'll pick back up here next time with some continuity. But for now, all I want to do is show you how to show that a limit does not exist. So example, show the limit as xy goes to 0, 0 of let's see, the one we're going to do is y squared sine squared of x over x to the 4 plus y to the 4 does not exist. So we want to show that this limit does not exist. Solution. So we can see that there's obviously a problem at the point 0, 0. We can't plug that in. We don't even know what to do if we plug something in anyway. So this seems like an interesting point for this function. So what are we going to do to try to find the limit of this function, or maybe show that the limit does not exist, which is what we're told to do. So we're going to evaluate along different paths. So think about this point, 0, 0. Where is this point? This point 0, 0 is right here at the origin. That's our point AB. It's this point at the origin. I'm going to approach that from the x-axis. So along the x-axis, well, that's when y is equal to 0. So if I approach this along the x-axis, I'll take the limit as x0 goes to 0, 0. And then I'm basically plugging in y equals 0, so that's 0 squared times sine squared of x over x to the 4 plus 0 to the 4, which is going to be the limit as x goes to 0. Because I don't worry about anything else, all that's changing is x. So x is just going to 0 from our ordered pair. So that's going to be 0 over x to the 4, which is 0 over a number, which is just 0. So along the x-axis, the limit is 0. Let's try along another axis. I'm going to try the y-axis. So along the y-axis, that's where x is equal to 0. So if I try along the y-axis, I get the limit as 0 comma y goes to 0 comma 0. And so that's going to be y squared sine squared of 0 over 0 to the 4 plus x to the 4. Sorry, y to the 4. Well, this is going to be the limit as y goes to 0. Let's see, sine of 0 is 0. 0 squared is 0, so that's 0 in the numerator over y to the 4, which is some real number, but not 0. This is just going to be 0. So I have two paths that give me the same limit. But I cannot claim anything from that. All I can say is that, well, these two paths give the same limit. Well, let's try to do something else. I'm going to try the line y equals x. So along the line y equals x, so the line y equals x, that goes to the origin. So I take the limit as x comma x, because y is equal to x, goes to 0 comma 0. And everywhere I see a y, I replace it with x. So that's x squared sine squared x over x to the 4 plus x to the 4. So basically every x or every y gets replaced with x. So that's going to be the limit as x goes to 0 of x squared sine squared x over 2 times x to the 4. And we can do a little algebra to simplify that. Limit as x goes to 0 of sine squared x over 2x squared. So this is an interesting limit. It's a single variable limit. We should know how to use or how to take this limit. We use L'Hopital's rule. So L'Hopital's rule. So this is going to be the limit as x goes to 0 of 2 sine x cosine x over 4x. So almost there. I can use a trig identity in the numerator and say that this is limit as x goes to 0 of sine 2x over 4x. And actually I still need to use L'Hopital's one more time because I still have 0 over 0. So L'Hopital's again. So L'Hopital's again, it's going to be the limit x goes to 0 of 2 cosine 2x over 4. And now plug in 0 because it's a continuous function. I get 2 times cosine of 0, which is 1, so 2 over 4, which is 1/2. Aha, I've got 0 along the x-axis, but 1/2 along the line y equals x. So what can I say? I can say the limit does not exist because I have 0 here and 1/2 here. So the limit does not exist because I have one path that gives me 0 and another path that gives me 1/2. So since not the same, if it does have a limit, they have to all be the same, no matter which path you take through the point. So that's how you show that a limit does not exist. So a little tricky. How do you show that a limit does exist? Well, you try the definition. That's hard, not super fun. You might try something else like the squeeze theorem. There is a multivariable squeeze theorem. I may present that right now and show you one example, and then next time we'll go over continuity and using polar coordinates to find limits. So the squeeze theorem very similar to the squeeze theorem for a single variable function. So suppose that, let's see, absolute value f of xy minus L is less than or equal to g of xy. For all xy, so for all xy in the interior of a circle centered at AB. Except possibly at AB. So just put that in there, except possibly at the point AB. The squeeze theorem then says if limit xy goes to AB, g of xy equals 0, then then limit of as xy goes to AB of f of xy equals L. So it's a very similar idea, squeeze theorem. So let's see how to use the squeeze theorem in an example. So for example, find the limit as xy goes to the point 0, 0 of the function 2x squared y over x squared plus y squared using the squeeze theorem. So using the squeeze theorem. Solution. Well, I've got to find a candidate. I got to find a candidate for the limit. So checking paths, x equals 0, y equals 0, y equals x squared, x equals y squared, all yield a limit of 0. So we conjecture or claim that the limit as xy goes to 0, 0 2x squared y over x squared plus y squared equals 0. So we will try to show the limit exists. Well, that means we need to show that the definition of a limit holds for this function now and this limit. First thing we do is we let epsilon be greater than 0. So it's some arbitrary positive number. And we want to find delta greater than 0 such that if, let's see, what is the condition? Square root of x minus 0 squared plus y minus 0 squared less than delta, then absolute value 2x squared y over x squared plus y squared minus 0 is less than epsilon. So we want to show this basically. So we got to find the right delta. Note, so number one here, this is using the definition. This is not what we're told to do, but we're using a definition. So note, absolute value of 2x squared y over x squared plus y squared would be equal to 2x squared absolute value of y over x squared plus y squared. Because the only thing that could possibly be negative there is the y, so the absolute value really just needs to go on the y. Also, note that x squared would be less than or equal to x squared plus y squared, which would imply that x squared over x squared plus y squared would be less than or equal to 1. So basically that means this thing right here is less than or equal to 1. So what we can say from that is that this would be less than or equal to 2 times the absolute value of y. Also note, whoops, that should be note. Also note that 2 times absolute value of y would be less than or equal to 2 times square root of y squared, which would be less than or equal to 2 times square root of x squared plus y squared. Because if I add something positive under that radical, it can only get bigger. So then I could say that this would be less than or equal to 2 times square root of x squared plus y squared, which is less than, or will be less than 2 times delta, because that radical is going to be less than delta. So now we just need to pick the right delta. So let delta be equal to epsilon over 2. So then this is equal to 2 times epsilon over 2, which is epsilon, which is what we needed to show. So that shows that the limit is equal to 0 using the definition. So this shows the limit is 0 by definition. That's not what we're told to do though. We're told to use the squeeze theorem. So I just have to find a function that bounds this function. Alright, so using the squeeze theorem, number 2, this is using squeeze theorem. So note again that absolute value of x squared y, or let's see, there was a 2, so 2x squared y over x squared plus y squared is equal to 2 times x squared absolute value of y over x squared plus y squared. And note, like we said before, that x squared over x squared plus y squared is less than or equal to 1. So this is less than or equal to 2 times absolute value of y. Furthermore, note that the limit as xy goes to 0, 0, 2 times absolute value of y would just be the limit as y goes to 0, 2 times absolute value of y, which would be 0. That's a continuous function in a single variable sense. So by the squeeze theorem, the limit as xy goes to 0, 0 of 2x squared y over x squared plus y squared is equal to 0. So 2 approaches, one using the definition, one using the squeeze theorem. All right, so we'll wrap it up there for today. We'll come back next time and look at some more examples of limits, trying to show that they exist or don't exist. We'll talk about continuity. We'll talk about limits using polar coordinates. That'll wrap up this section, and then we're going to jump over to chapter 15. We actually come back to chapter 14 in our next calculus class. So have a good day. Talk to you guys later.